Hello! In this video, we consider the following problem. Suppose a ball is kicked into the air above a hill that is angled downward at an angle phi. And we'll say that when the ball is kicked into the air, the ball is kicked with an initial speed v0, and of course the acceleration due to gravity is downward at 9.81 meters per second squared. So these are the three quantities that we are given. The whole goal is to figure out what launch angle do we kick the ball at so that we get maximum horizontal distance traveled. So let's first visualize what this problem is asking.
So this is essentially the hill that we are kicking the ball over. Now, as you can imagine, if we kick the ball at a steep launch angle, then the distance that the ball travels isn't going to be that far. Likewise, if we kick the ball at a relatively shallow launch angle, then the ball also isn't going to go that far. But if we kick the ball at a launch angle between that, as you can see about right here, the ball will end up going a maximum distance. Right, you can imagine varying the launch angle. So it turns out this orange path is the path that you kick the ball through to obtain the maximum possible distance traveled. Right, so essentially the whole goal is to figure out the launch angle of this orange path.
So to figure out the launch angle that yields maximum distance traveled, what we want to do is we want to figure out r as a function of theta. And in the language of calculus, to figure out the value for theta that yields a maximum value for r, we want to find theta when dr over d theta is equal to 0. Because that will give us our critical point. And we want to show that that critical point is a maximum. So that's really what we want to do. So let's first figure out r as a function of theta. To figure that out, we're going to consider both the horizontal and vertical motion of the ball while it's in the air. To consider both the horizontal motion and the vertical motion of the ball, let's break up the velocity vector into its components. Here we have the horizontal component, and here we have the vertical component. The horizontal component I'll label Vx0, and the vertical component I'll label Vy0. Now, when it comes to projectile motion problems, when we're analyzing the horizontal motion, we're dealing with constant velocity. And when we're analyzing the vertical motion, we're dealing with constant acceleration. So let's first analyze the horizontal motion. Since we're dealing with constant velocity, well then we can use the equation horizontal displacement equals horizontal velocity times time. So if we consider the displacement of the ball from this point to this point, well, the horizontal displacement is just r. And the horizontal velocity is constant, so the horizontal velocity must be equal to the initial horizontal velocity. So I'll replace Vx with Vx0, and t is just the time it takes for the ball to go from here to here. Now, using trigonometry, we have Vx0 equal to V0 cosine theta. So this is what we get when we analyze the horizontal motion of the ball. Now let's analyze the vertical motion of the ball. Well, we're dealing with constant acceleration in this case, so we can use one of our kinematics equations. And the kinematics equation we're going to use is the following. We're going to use this kinematics equation. Now, the vertical displacement of the ball is the vertical displacement from this point to this point. Notice the ball moves downward, so the vertical displacement is negative. What that means is the vertical displacement of the ball must be negative h. And if we use trigonometry, we have Vy0 equal to V0 sine theta. And the vertical acceleration is pointing downward, so the vertical acceleration is negative, and it must be equal to negative g. So this is what we get. Now, we can actually re-express h in a different way as well. Using trigonometry, we can express h in terms of r and the angle of the hill, phi. Now, actually, this triangle is drawn so that these two lines are parallel. Right? Because really this is a horizontal line, this is a vertical line, this is a horizontal line. Right? So these two lines are parallel. And from geometry, because these two lines are parallel, well, these two angles must be congruent, right? They're congruent alternate interior angles. So since this angle measures phi, this angle must also measure phi. So then, applying trigonometry to this right triangle, we have h equal to r tangent of phi. So this is what we get when we analyze the vertical motion of the ball. So at this point, we have two equations. In total, these two equations consist of 6 quantities, which I'll write up here. These two equations in total consist of these 6 quantities. Remember, these 3 quantities are constants, right? We're given these 3 quantities in the problem, right? And these 3 quantities are variables. Remember, the whole goal is to get an equation that relates r and theta. So what we want to somehow do is combine these 2 equations into a single equation, and in the process, we eliminate the variable time. And to do that, what we're going to do is we're going to take this equation, solve for time, and then substitute that into the other equation. So to solve for time in this equation, we're just going to divide v naught cosine theta to the other side. And so we get this. And now let's plug this in to the other equation. So this is what we get when we plug this value for time into the other equation. And now notice the v naughts cancel out. And we know sine theta over cosine theta is equal to tangent theta. And now let's take this term and combine it into a single fraction. In the numerator, we're going to have g r squared. In the denominator, we're going to have 2 v naught squared cosine squared theta. So this is what we get. And now, notice all 3 of these terms contain r. So we can divide r on both sides, and the r's will cancel out, and r squared divided by r will just leave us with r. So this is what we get. And at this point, we can actually algebraically solve for r. So let's do that. To do that, we're going to add this guy to the other side, and we're going to add tangent phi to the other side. So we get this. And next, let's multiply 2 v naught squared cosine squared theta to the other side. So we get this. And next, let's divide g over to the other side. So we get this. Now notice, I've re-expressed this guy in a different way, because we're going to distribute 2 cosine squared theta across this parentheses. Now remember, tangent of theta is equal to sine theta over cosine theta. So when we distribute 2 cosine squared theta across this parentheses, we see that cosine squared theta divided by cosine theta is equal to cosine theta. So when we distribute this guy across, we get this. But actually, 2 sine theta cosine theta is a trig identity. It's the trig identity for sine of 2 theta. And so this is what we end up with. And so at this point, we have combined these 2 equations into a single equation which relates r and theta. And actually, we have eliminated time. So we're all good. Now, remember, the next step is to take the derivative of this guy and set the derivative equal to 0. From there, we'll solve for theta. And the value for theta that we get will correspond to a critical point. And so, from there, we're going to show that that critical point is a maximum. So now, at this point, let's take the derivative of this guy. before I erase this, let me just rewrite this back at the top before we take the derivative. And now let's take the derivative. Now, v naught squared over g is just a constant, so let's pull that to the outside. And now we're trying to take the derivative of sine of 2 theta plus 2 tangent phi cosine squared of theta. So let's start with the derivative of sine of 2 theta. Well, we know that the derivative of sine is cosine. And then by the chain rule, we just multiply this by the derivative of 2 theta. And the derivative of 2 theta is just 2. Right? So now let's figure out the derivative of 2 tangent phi cosine squared of theta. Well, 2 tangent phi is a constant. So let's pull that to the outside. And from here, we want the derivative of cosine squared of theta. So we're taking the derivative of something squared. In general, the derivative of u squared is 2u. So the derivative of cosine squared of theta is 2 cosine theta. But then we apply the chain rule. We multiply this by the derivative of cosine theta, which is just negative sine theta. So this is what we get when we take the derivative of these guys. So now, let's just clean this up a little bit. So this is what we get. Now actually, remember, sine of 2 theta is equal to 2 sine theta cosine theta. And we see the identity for sine of 2 theta in this second term. Notice this guy is equal to this guy, which is equal to this guy. So really, we can replace this second term with this guy. And then we can just factor out a 2. So this is what we get when we take the derivative with respect to theta. And now we want to set the derivative equal to 0 and solve for theta. And so let's do that. When we set the derivative equal to 0, well, first of all, 2 v naught squared over g is positive. So if we divide it on both sides, it goes away. So we're left with 0 equals cosine of 2 theta minus tangent phi sine of 2 theta. So let's just add this guy to the other side. So we get this, and then let's divide sine of 2 theta to the other side. So we get this. Now, cosine over sine is equal to cotangent, right? So really, this is just cotangent of 2 theta. But then actually, we have a trig identity that relates cotangent to tangent. And that trig identity is cotangent of x is equal to tangent of 90 degrees minus x. So we can replace cotangent of 2 theta with tangent of 90 degrees minus 2 theta. And so we have tangent of an angle is equal to the tangent of another angle. Now, in general, if we have tangent of x equal to tangent of y, does this imply x is equal to y? Well, in general, no. This is not necessarily the case. However, we can be sure that tangent of x equals tangent of y implies x equals y if x and y are both angles between negative 90 degrees and 90 degrees. Right? This is because if we consider the function tangent of x on the interval negative 90 degrees to 90 degrees, we know it looks something like this. The tangent function is a one-to-one function. Because of that, we can be sure that this statement is true. And so what we're going to do is we're going to show that phi and 90 degrees minus 2 theta both lie in the interval negative 90 degrees to 90 degrees. From there, we can use this fact to conclude that phi is equal to 90 degrees minus 2 theta. Now, we already know that phi lies in the interval negative 90 degrees to 90 degrees, right? Because phi is just the angle of this hill, and phi is just an angle between 0 degrees and 90 degrees. Right, it makes sense for the angle of the hill to be between 0 degrees and 90 degrees. So we already know phi is an appropriate angle. It lies in this interval. So we're good with phi. So then now all that's left to show is that 90 degrees minus 2 theta lies in this interval. And to show that, first of all, how much can theta range by? Well, when we kick the ball into the air, it makes sense that we could kick the ball at an angle between 0 degrees and 90 degrees. So we're just going to say that theta ranges between 0 degrees and 90 degrees. And now let's just modify this inequality so that we get an inequality for 90 degrees minus 2 theta. So if we take this inequality and multiply 2 on all three sides, we get 2 theta lies between 0 degrees and 180 degrees. And then let's just multiply negative 1 on all three sides. That'll flip the signs of the inequalities, and so we get this. And then let's just add 90 degrees on all three sides. So we get this. And as you can see, 90 degrees minus 2 theta lies between negative 90 degrees and positive 90 degrees. So it lies in this interval. And so at this point, we see that both of these angles lie in this interval. So according to this statement, this implies phi must be equal to 90 degrees minus 2 theta. And now let's just solve for theta. We'll add 2 theta to the other side, we'll subtract phi to the other side. So we get this, and then if we divide 2 on both sides, we get theta equal to 45 degrees minus phi over 2. So this is the launch angle that we were looking for. And so what we see here is, when we set the derivative equal to 0, we have theta equals 45 degrees minus phi over 2. So at a launch angle of 45 degrees minus phi over 2, we have a critical point. And now we want to show at this launch angle, we have a maximum value for r. And to show that, here's what we're going to do. We're going to show if the launch angle is between 0 degrees and 45 degrees minus phi over 2, the derivative is positive. And if the launch angle is between 45 degrees minus phi over 2 and 90 degrees, the derivative is negative. If we can show that, then that will tell us if we increase the launch angle starting from 0 degrees until we reach 45 degrees minus phi over 2, the distance traveled will increase. Once we have a launch angle of 45 degrees minus phi over 2, the derivative will be 0. And then if we increase the launch angle anytime after that, well then the derivative will be negative, and so it decreases. That will tell us we increase and then we decrease. Then the turning point happens when we have a launch angle of 45 degrees minus phi over 2. So that tells us we will have a maximum distance traveled at a launch angle of 45 degrees minus phi over 2. So let's show this. We'll start with the case that theta is between 0 degrees and 45 degrees minus phi over 2. Right? In this case, we want to show that the derivative is positive. So let's just write out the derivative again. And what we're going to do is, we're going to factor out sine of 2 theta from this parentheses. If we do that, the first term is going to be cosine of 2 theta over sine of 2 theta. The second term is going to be minus tangent of phi. And actually, cosine over sine is just cotangent. So this is just cotangent of 2 theta. And remember, cotangent of 2 theta is just tangent of 90 degrees minus 2 theta from this identity. So this is what we have. Now, we want to show that the derivative is positive. And to do that, well, let's modify this inequality. What we're going to do is we're going to multiply 2 on all three sides. And if we do that, we get 0 degrees is less than 2 theta, is less than 90 degrees minus phi. And now focusing on this inequality, we're going to subtract 2 theta to the other side and add phi to the other side. So we get phi is less than 90 degrees minus 2 theta. Remember from earlier, these two angles lie in the open interval of negative 90 degrees to 90 degrees. Now, since tangent is an increasing function on this interval, this implies that the tangent of phi is less than the tangent of 90 degrees minus 2 theta. And so, this difference is positive. Now, since theta is between 0 degrees and 90 degrees, 2 theta is between 0 degrees and 180 degrees. The sign of anything between 0 degrees and 180 degrees is positive, so this is positive. And of course, 2v0 squared over g is positive as well. So overall, when we multiply these guys together, we have that dr over d theta is positive. And so, this shows if theta is between 0 degrees and 45 degrees minus phi over 2, the derivative is positive. So now, let's consider the other possibility. What happens if the launch angle is between 45 degrees minus phi over 2 and 90 degrees? We want to show that the derivative is negative. So, first of all, let's write out the derivative again. And just as we did before, we can factor out sine of 2 theta from this parentheses, and we can apply this identity to obtain this. Now the whole goal is to show that this guy is negative. Now, if we modify this inequality, what we're going to do is we're going to multiply 2 on all 3 sides. That will give us 90 degrees minus phi is less than 2 theta is less than 180 degrees. So if we focus on this inequality, we'll add phi to the other side, subtract 2 theta to the other side. So we get 90 degrees minus 2 theta is less than phi. Remember, both of these angles lie in this interval, and tangent is increasing on this interval. So this implies tangent of 90 degrees minus 2 theta is less than tangent of phi. And so because of that, this tells us that this difference is negative. Right, and just as before, sine of 2 theta is positive, 2v0 squared over g is positive. So when we multiply these guys together, we have that the derivative is negative. And so, on this interval, the derivative is negative. And so, let's put this all together again. On this interval, the distance traveled increases. When the launch angle was 45 degrees minus phi over 2, the derivative is 0, and on this interval, the distance traveled decreases. So we increase, then we decrease. We see that the maximum distance traveled occurs when we have a launch angle of 45 degrees minus phi over 2. And interestingly, although it makes intuitive sense, the launch angle that yields maximum distance traveled in this case is less than 45 degrees. If you recall, 45 degrees is the launch angle that yields maximum distance traveled over a flat surface. And so yeah, that's pretty interesting. And yeah, that's pretty much it for this video.